All right, awesome. Thank you everyone for joining us today. Welcome to our webinar, Expand Your Senses with Neosensory and Edge Impulse. We've got Dr. Scott Novich and Jan Youngboom here with us to give you more information about building an Edge Impulse model and connecting it to the Neosensory Buzz. So a little bit more about our speakers today. Scott is a co-founder and CTO of Neosensory. He is an electrical and computer engineer and neuroscientist who received his PhD in Dr. Eagleman's lab. His thesis on non-invasive sensory augmentation provides the foundation for Neosensory's technology. We've also got Jan here. He's an open source developer and technology evangelist working on tinyML as the CTO of Edge Impulse. So over the past years, he's gone up and down the stack from embedded to web and everything in between. He's a strong believer of open source, has written thousands of patches for open source projects. You'll also see Jenny Stenhouse, a developer advocate for Neosensory here in the background. She's going to be helping answer some questions that come in through the Q&A during the webinar. So like usual, we'll have a 10 to 15 minute Q&A at the end where we'll have Jan and Scott answering your questions. If you do have questions during the webinar, feel free to post them in that Q&A section at the bottom of your screen, and we'll try to get to as many of those as we can before the end of the event. This is a webinar associated with our contest, the Expand Your Senses contest on Hackster. So I'll post a link over there if you aren't familiar with that, and you can kind of learn a little bit more through that. So thanks again for joining us, and I'm going to let Scott get us started.
Awesome. Thanks, Katie. Well, thanks everyone for joining us. Really excited to be catching up with you. I think we can generally skip the CTO intros from us, but I do want to highlight the amazing headshot that Jan managed to dig up of me from the depths of the internet. That's pretty incredible, Jan. It's pretty awesome. Totally not weird. It's awesome. But anyways, so moving on. So
what is going on here, Scott? What is going on here?
Yeah, it was from there was this photographer who just came into our office when we were just starting the company and wanted to do all sorts of weird headshots with employees with our technology. This is definitely one of the weirder ones, but there are some also really awesome ones. I think I'll give him shout outs. Brian Goldman, check out his website. He has some cool photo art on there. Anyways, so also as Katie mentioned, this is part of our ongoing contest on Hackster. And yeah, so Edge Impulse and Neosensory teamed up on this because I think our technology is a pretty amazing merger that can create some really powerful, cool applications. So just as a little bit more of an intro about what we do. So Neosensory develops wearable, non-invasive sensory augmentation devices. And if that sounds like a mouthful, it kind of is. But generally, we develop devices that try and enable people to jack information into their brains through non-invasive means. So our first product that we're selling right now is called Buzz. It's a wristband that has 4 vibrational actuators around the wrist, and you can plug in whatever data streams you want and encode that information using vibration to get that to the brain to hopefully train up on new senses. And I'm sure Jan will talk a bit about Edge Impulse in a second, but Edge Impulse is a platform that I'm super enamored by. They enable you to train and deploy really easily powerful embedded machine learning models, which I think is a really great marriage of our 2 technologies. So I'm actually not going to get too much into the neuroscience behind our device today. We actually ran a webinar previously on this. You can find it. You can either go to these URLs or you can just easily search for the webinar video on YouTube. If you just search for Neosensory webinar, would highly encourage you to check that out if you are in the competition or thinking about joining it. And I think, by the way, as an aside, there's like 9 days left in the competition, so totally enough time to come up with that killer app and win. So definitely join in on that. But yeah, so definitely check out the webinar. In that we go a lot more into the details of the neuroscience and philosophy behind designing effective applications for this device. But I will quickly say, so whenever we initially tell people that, oh, here's this wristband that has vibrational units, people's minds tend to kind of gravitate immediately towards kind of notification-based applications. So like, oh, I can just know when I'm receiving a text message or an email, I can create cool applications like that. But that's totally underutilizing the power of this technology. what you can totally do that, but what we're really after and what this technology enables is trying to give people new senses of real-time data streams. So for example, if you wanted to plug in the sensor information from a drone and feel what it's like to be an extension, to like feel like the drone's an extension of you, crazy stuff like that, or some other, or just because we're talking about Edge Impulse today, an example might be like if you have a bunch of sensors in your beehive and you want to know like the sentiment of, you want to know like how your bees are, you want to like classify the sentiment of how your bees and your beehive are feeling at any given point in time by doing like some computer vision or something crazy on like the on like a camera in your beehive. I don't know. Anyways, so I'll just leave that there, and again recommend people check out the webinar for more thinking on how to design these sorts of applications for our technology. Programming our technology is really straightforward. You can control Buzz over anything that supports a Bluetooth low energy link. We have SDKs. They make things a lot easier, but they're not required. So if you just check out our API documentation, you can work just with that because it's a standard protocol. But we currently have SDKs available for the Adafruit Arduino Bluefruit series, like the Feather and the Feather Sense. We have an SDK for Android, and we have an awesome community contributed SDK for Swift. So that would be for like your Apple Watch or iOS, stuff like that. Shout outs to our developer community member, Chris Bartley, for putting that together. So yeah, definitely head over to our developer website, neosensory.com/developers, and that's kind of like a good launching point for all of this stuff. And then, yeah, we also have a ton of other resources there to help you get started with those things. So check out our Neosensory blog, where we have a bunch of walkthrough and tutorials of different cool applications that we've made, like being able to feel satellites whizzing by above you, or feeling infrared, getting infrared vision through the wristband, stuff like that. All right, and yep, last before I hand this off to Jan to dig into the really awesome demo that he put together with our wristband and Edge Impulse, I'll just say join our fantastic Slack community. A bunch of the Neosensory people are hanging out there. A lot of really cool people on there. Again, you can access that through our developer site, but definitely hop on there anytime if you need to reach us for help, or you want to just talk about ideas with us or other people. Always happy to talk to members of the community. And with that, yeah, I'll hand it off to Jan.
Thanks, Scott. Hey, yeah, and I mean, I have to say, I've been playing around with the Buzz for the last couple of weeks. It is really weird at first, right, to hear sounds kind of as vibrations, but it's pretty awesome technology, and I kind of can't wait to see what you guys are all going to build with this in the contest. And I think that what we can do with Edge Impulse, as Scott said, is really complementing that. So I hope to, in the next 20 minutes, give you a real taste of that in the presentation. And then we'll dive actually into building something, combining these two technologies, which is going to be great. So if you're thinking about if you want to program something, and just going to Scott's kind of first example of kind of underutilizing the Buzz, then kind of one of these first things of, there's something happening, I want to get an event, and I let my Buzz vibrate. That is really easy to do because it's really easy for us to understand this. I might say I have a temperature sensor, or I want to know the temperature, and I can do that with a simple thermistor or a digital thermometer. And I want to send an event to the Buzz whenever the temperature drops below 10 degrees Celsius, what we see here on the left. Really easy to do. I grab a temperature sensor, I grab a little bit of code to read data from that, and then whenever the temperature is above or below this threshold, I send the message to the Buzz. Easy. If I'm a developer, it's probably the IoT 101 that I built. Some things, though, are incredibly hard. If I have a, let's say, kid here that says something like Neosensory, and then I want to have my Buzz actually respond to that, that is incredibly hard to do. There's not a sensor that I can buy right now from DigiKey that will send me an interrupt whenever I hear the word Neosensory. There's millions and millions of sounds around us, and trying to distinguish the ones that interest us, that is really, really hard to do. Not just in general, but yeah, it's not just hard in general, but it's also hard to do it even even on large-scale computers, let alone on really small ones that actually need to communicate with a computer sitting on your wrist. But there is a solution to that. And we find it in a new way of programming. So if I normally write code, let's say I have sensory inputs, my temperature sensor, I have rules, I have a threshold of -10 degrees, and depending on that, the outcome should be 1, the buzz should buzz, or no, the buzz should not buzz. That's relatively straightforward. I can write that up, and that's how we currently code. Machine learning is is an interesting approach to the same problem where you have the input and you have the outcome, but you don't know the underlying rules. So in our case where the kid is screaming Neosensory, we can record audio of someone saying Neosensory. We can tag that with the outcome here should be, the buzz should vibrate. Find me the rules that map that. So I create a large data set of people saying Neosensory, people saying different words, noise, traffic, etc. Everything that my sensor can actually grab. And I combine this input with the outcome, and I let a machine learning algorithm find the rules for me. So this is being used in a wide variety of cases, recommendation engines, fraud detection on credit cards, games. I mean, for me, the very first time that I heard about machine learning was probably with Deep Blue in 1996, when an IBM computer actually beat the best human player in chess. Then going forward, a couple of years later, I guess everyone still remember that. If you haven't seen the documentary, go do it on Netflix about AlphaGo, where a team at Google DeepMind managed to build a machine learning algorithm that could actually beat the game of Go. But for me, all of these things, like from the very first time that I heard about machine learning, and I started realizing that indeed, well, this is a really great way when I do have an input and an outcome, but I don't have the rules, is that we always associated machine learning with this large scale data centers full of GPUs crunching numbers. And at first sight, that actually does not seem compatible with the idea of having a low power device sitting in your wrist actually responding to things. Now, as Scott said, you can control the buzz over Bluetooth, so no one is stopping you from building a shed next to your house, filling it with GPUs, and then whenever it hears something, sending a message to the buzz, but this is not really scalable if you want to do this at scale. So there's one thing that I want to stress when we talk about machine learning, and machine learning is a really powerful thing which finds the hidden correlation, but after it's done with that, it's in the end, it's just mathematics again. So let's look at a small experiment here. Let's say that you want to have your buzz vibrate whenever it feels water boiling. Now you might know that there is a correlation between altitude and the boiling temperature of water, but you don't know the exact correlation between these. So you start collecting data. So you get a temperature up to 98 degrees to water, you're at 0 meters altitude, and you note down, okay, water at this point is not boiling. You up the temperature of the water to 102 degrees, we're still at 0 meter altitudes. Now the water is boiling, great, that's my second thing. Now the interesting thing is I go mountain climbing, I'm 2.2 kilometers high. Once again, I bring the temperature to 98 degrees, but in this case, the water is boiling. So there's definitely a correlation between these two things. So I keep doing this and doing this and doing this until I have lots of readings. In this case, I have data, in this case, two sensor axes, and I have some labels, whether it's boiling, yes or no. And I can train a machine learning model to find this correlation, find the rules of how temperature and altitude contribute to the boiling point of water. And what we do with an ML model is we find a function, just a mathematical function, that most accurately maps the data to the label. So how can we find a function that has the least error when mapping these temperature and altitude data to the label that comes out? And that takes lots of trial and error because our ML model doesn't know anything about temperature or altitude or what the hell water even is. But the great thing is that after it finds it, and it could be as simple as this, after it finds a formula that works nicely, this is just mathematics. This is just a math function. There's nothing special in the final formula that an ML model finds. It just finds the rules, and if the rules are relatively simple, it's just math. And fortunately, microcontrollers are incredibly good at math already. And that means that when it's just math and microcontrollers are really good at math, we can just run this on a wide variety of small devices. Finding the initial formula, that takes a long time. That takes lots of compute, probably run it in a data center. But afterwards, we have something that we can run relatively efficiently on really small devices. And that all of a sudden pushes much more complex data processing to small computers that are all around us, like, for example, the one that's sitting here in the Buzz. So this kind of movement was kickstarted, I think, by Pete Warden at Google, and later by Neil Tan, who was working with me at ARM, when both Pete and Neil kind of at the same time realized that there are places where machine learning was already being applied 3 years ago on really tiny devices. So if you have your phone, an Android phone in this case, and you say, okay, Google, you can't have the main CPU be awake all the time, just waiting and listening on the microphone until someone finally says, okay, Google, and stream that to Google to do the interpretation there. No, you need to run that on a separate chip, in Google's case, a DSP, because that's the only way you're going to hit your power consumption constraints. So they have a very low power, very small chip sitting next to the main processor that is just listening for this OK Google keyword. That's the moment the main processor wakes up, and then they start streaming your query to a central location. And Pete, after the acquisition of his own company, went into Google, realized that there was a team working on this, and saw that they actually ran this model in 20 kilobytes of RAM. It was like, hey, that's an interesting case. And he kind of figured also out that if you just focus on the inferencing, just focus on executing this mathematical formula in the end after you found it, this is not a very intensive process. It's just a mathematical function with lots of parameters. So in my team at ARM, the team in Google, we started working, okay, now that we have that mathematical formula, that's great. How can we make it run even faster on general purpose hardware? So a couple of things that people realize is that while you're trying to find this formula, you need very high accuracy, because you constantly change like all these parameters a little bit and you see whether this gets you a better outcome. But once you finally found that, you can throw away lots of this accuracy, because it doesn't matter too much. If you have 100,000 parameters, they don't need super high precision. You just need the basic flow, and you get kind of 99% there. We realized that lots of these parameters are important while you're trying to find the formula, but then after don't contribute much, so you can just prune them out. And we realized that we can use hardware optimized paths. Even a Cortex-M microcontroller these days, we're really under a small thing like fits in 1 square centimeter, has vector extensions to push multiple instructions to the queue at the same time. So ARM, Google, but also other companies like Synopsys have been adding support in their DSPs for these types of operations. So cool. So where does Edge Impulse come in? We think that machine learning is incredibly cool. We think that machine learning on embedded systems makes lots and lots of sense, because as Scott said, there's all of a sudden a lot more things that you can actually distinguish. It's not just what is the current temperature, but rather, do I hear birds tweeting? How many bees are in my beehive at the moment? Even predictive things, like based on the current sensor data of my fridge, what do I think the temperature is going to be 10 minutes from now? And now you can start feeling that already. So when I founded Edge Impulse, we figured we want to build these tooling specifically for engineers. We want to make tooling that lets engineers build these types of machine learning algorithms that operate on real sensor data, and do that not just for data scientists, but for people that build this on a day-to-day basis. So we started out with really the first thing is, how do I do data collection from real devices? How do I do a signal processing pipeline? Machine learning can be a really black box where you throw random data in and a model comes out, but there's no way to check whether that model is actually correct easily. But we do understand signal processing around that. If I have audio, I know that I can make a spectrogram that shows me time frequency information. So we'll help you guide through that, all the way to verifying your model and finally deploying that. The nice thing here, I think, is that just like what Neosensory is doing. We have really nice integration points as well, including Arduino libraries. And together with the Neosensory Arduino library and the EdgeImpulse Arduino library, all of a sudden you can have something that responds to really complex sensor data, and then does something here directly in your wrist, which I think is an incredibly powerful combination. It's free for developers. We have an enterprise plan for larger customers, but you can just get started here today. The source code that you put out, everything that we show is open source and open, and royalty free as well. So there's nothing stopping you from actually building something really, really cool for this contest. And what we're going to be focusing today here is really on audio, but I'd like you to also take one step back after and realize that you can do a lot more. Like, yeah, you can respond to keywords or to your doorbell, but in the end, they're just events. You can also start thinking, so there's a couple of things that I think are cool that you could explore here. One is visual cues. Do you want to have a different vibration sound when a human is approaching your door versus a dog? Do you want to see the number of people that are walking by? Whether your fridge door is open or closed, you can start feeling those kinds of things. Everything where you want a visual cue. Also, we'll focus on classifiers today. So I hear a second of audio. Is this a certain audible event? Yes or no? Which is great. But you can also think about regression cases. So where you predict a scalar value. So one of the cool things that I was hacking on the other day is have a microphone that knows how far my sink is open. So if I open it all the way, it's 100. If it's all the way closed, it's 0, and everything in between, which is kind of cool. It's like a water flow meter, but then just by audio. That is something where you predict a scalar value. And because you have the 4 motors sitting here in the bus, you can actually change how much the vibration is depending on how far you have opened or closed your own faucet, which I think is it's kind of fun and has lots of really cool applicabilities, much wider than outside of your home. So think a bit about that. Think about not just audio, think about visual cues as well, and start thinking a little bit how regression might be able to help. So yeah, Scott will talk a little bit about their SDKs and how you can really get started with the Bluetooth SDK here.
Sure. So thanks, Jan. So it's really straightforward. I'm sorry for throwing up like a bunch of code garbage on your screens right now. But hopefully we can just break this down into a few simple areas. And this is generally the same structure that it'll run into for most of our SDKs. And kind of technically, even if you use the API directly, it's just there's a little bit additional coding involved. But so this is the example SDK walkthrough we used for our Neo Bluefruit SDK. So this would be for devices like the Adafruit Feather NRF52, stuff like that. So generally, you just start by setting up a few key callback functions for the Bluetooth interface. So you just want to do something special once you know you're connected. You might want to do something special if you know the buzz sends back a message to you, which it can do. And then just do something special if it's disconnected. So that's about it. So here's an example. Callback function for when you're connected. There's just a few initialization commands you need to send over. You set up the developer access to the developer commands, which enables Buzz to accept commands like being able to vibrate a motor. And then you stop the onboard algorithm that runs on the Buzz itself. So something I didn't quite mention yet, but the Buzz itself runs an onboard algorithm for mainly our deaf and hard of hearing population that takes sound from the environment and maps it to vibration around your wrist in real time. But developers, like I said, can kind of can pause that algorithm and plug in their own data streams. So you just send a few initialization commands once you know you're connected, and you set up the Buzz you set up the Arduino device to print out any messages to your console that Buzz is receiving, and then at that point you can just basically you can just tell the Buzz to vibrate when and however you want. So in our demo example, there's this like little rumble pattern function. So it creates a series of motor commands or motor patterns for creating the sensation of a rumble on the wrist. And all you need to do is then in the rumble function, you see this Neo Bluefruit.vibrate motors. all you need to do is just send over this array of frames, which is literally an array of just concatenated motor values on 0 to 255 for how strong the motor should be. So in sets of 4, so if you had an array of 4, that each of those 4 elements would map to 1 motor on the wrist and how strong those are. But you can actually string those together to have 4, 8, 12, 16, any multiple of 4 frame that you want to send over at once, and it'll play it back as an animation on the wrist. So you create your vibration functions, and then in your loop, you just trigger it to vibrate whenever you want. So in this example, all that's happening is, as you can see, it's choosing a motor to vibrate. It's setting the intensity value for that motor. So you can also just send over a single motor and an intensity value as well. And it's looping through all the motors and the intensities. And when it finishes looping through everything, it then sends these rumble patterns and then starts over again. So pretty straightforward, and that's about it. But now, Jan, you took this effectively, you retooled it for the Nano 33 BLE, and you integrated Edge Impulse into it, which is super awesome, and would love to see how you did that.
Absolutely. Thanks, Scott. Yeah, so we'll be publishing we tried to get the Nano 33 BLE Sense SDK ready for today. We haven't done it yet, but we'll follow up soon, and hopefully in the email you get after the event, we'll have that published. But yeah, let's actually put this all into practice, and let's build a model that will actually do stuff based on what we hear in the microphone, which is great. So yeah, as said, Edge Impulse is a tool specifically made for embedded engineers to let you build machine learning models that operate on sensor data. How I kind of see it is there's 3 types of things you want to do typically. You either want to classify, so what is happening around me at the moment. You want to kind of predict something. Let's say you want to predict the future based on current data, what's going to happen next. Or you want to detect anomalies, like when is something happening that is out of the ordinary. So Edge Impulse lets you build these types of models straight here from a visual UI and get data from a wide variety of sensors, and then finally deploy that to dev boards or kind of anything with a C++ compiler. Today, what we're going to be looking at is a classification pipeline, specifically on audio data. So a small demo, kind of what we want to do, hello world, but then actually by voice. So we're going to be building a small project where if someone says hello world, we'll make the buzz actually vibrate. So the first thing that we need here is data. As said, when you're building a machine learning model, you collect raw data, you combine it with the outcome, what should this be classified at, and the machine learning algorithm will find the underlying rules between them. So let's actually start with collecting some of the data. So we get the data acquisition. You know, I cheated a little bit. I collected some data already last month. We'll go here. Cool thing here, so you can use a wide variety of dev boards to collect data. But if you're dealing with audio data, you can do this straight from your phone as well. So you go to show options, show QR code, and we'll scan it with my phone. So now I have my phone here, and I can say I want to collect some Hello World samples. Naturally, this can also be your doorbell or the ping of the washing machine, but any audible event. Let's start. Hello World. Hello World. Hello World. Cool. So now I have a sample, but I see 3 Hello World samples here. So I want to cut those individual samples out. So I go here, I say split sample. We automatically find the places with the highest energy in your signal, crop it out here in 3 cases. And in this case, you can't hear what I'm saying, but this is definitely Hello World, this is Hello World, and this is Hello World. So I split these, and now I have 3 of these. Beautiful. Similarly, I also want to have some unknown words, so things that are not Hello World. And that's because otherwise, if you only have noise, background noise, and the keyword that you're looking for, there's a high chance that the model will just trigger on any human speech. rather than on just on the keyword that we have. So let's do that as well. Neosensory, Edge Impulse, Hackster. So once again, 3 of these. I'll split that up as well. We'll find the 3 things. I'm going to move this a little bit if I see it's out of touch. Beautiful. That's great. We do have, and I think that's cool, if you want to build something here, we have basic data sets of noise and unknown words already. So here's the thing, like I collected 8 minutes of Hello World data. That's already basically all my colleagues having to say something. I don't want to do that also for noise and unknown words. So if you go to docs.edgeimpulse.com, there is the, under data sets, there's a keyword spotting data set. And this one has already unknown and noise data. So that's an easy way to get started if you want to do something. The noise data in general is very useful. If you want to build a doorbell sensing device, then the noise data set is always very useful there already. So all right, so I have my data, in this case, 20 minutes of data, my training set. And then I also have a test set. So that's data that I keep separate while I'm building my model. And I can use it to verify whether my model is going to work nicely, yes or no. I want to build a pipeline. So we always start here by saying, well, what is the type of data that we're looking at here? So we're looking at time series data. And then we want to do some pre-processing on that data. 1 second of audio data, what we're looking at here, has 16,000 features. And that's a lot of features. And those features are relatively noisy. You see little spikes everywhere. So by pre-processing that data, we can already highlight some interesting features. So what we typically do is we add a spectrogram here. And a spectrogram contains time and frequency information. And that gives me a couple of things. One, it makes the number of features a lot smaller by doing some pre-processing. We can go from 16,000 to maybe 2,000 features. And we really lay this out in a nice way. We say, okay, all the time data is always on the horizontal axis, all the frequency data on the vertical axis, and that is going to make it a lot easier for a machine learning model to find the correlations. Now we can do something much cooler here if you know that this is human speech, and that's how we create a male frequency septal coefficients spectrogram. And what we do there additionally is that we don't just make a normal spectrogram with time frequency information, we actually highlight the frequencies that we know are interesting or are being used in human speech. And then we throw away everything else. So we throw away all the noise and we get a spectrogram that just highlights the interesting things what we say. So if I look at, this was Hello World. It's not, I don't know how clear it is on the stream, but you see here, this was, so we see Neo here, Sen, saw, re, 4 syllables, relatively low. And then if I go to Hello World, I'll see Hello World, but more as one little thing here rather than as these 4 individual syllables that we see here. If you can't see it by hand, that's okay. We're going to throw a machine learning algorithm actually at this to help you a little bit here. One of the cool things here that we show always is, because we care about how this is going to run on device, we'll show the on device performance here. So if you start playing around, you say, oh, well, what if I want to have a longer FFT? Maybe that works better. Well, that jumps, my processing time jumps with 100 milliseconds extra, and it might not be worth it to do that. But here we want to analyze a second worth of audio, and we spend 212 milliseconds here on the Arduino Nano, which is totally fine. Then we have something cool. So how well does my data set actually, how good does my data set actually look like? It's really hard to do that if you have 16,000 data points, or even if you have all these spectrograms, because I have, in this case, 27 minutes worth of audio data, and lots of frames. So what we kind of do as a cool feature, I think, in Edge Impulse, for me, one of the most useful features, is that after we generate all these spectrograms, we have a dimensionality reduction algorithm that then tries to compress all these spectrograms in 3 axes and then plot all your data in one three-dimensional graph. And that is going to show some interesting things. First of all, if I plot all my hello worlds against all my unknown words, so everything that was not hello world, you already see that it separates very nicely. And that's great because that's what we want, right? We want to have this separation very nicely. But there are a couple of places, a couple of things in my data set that look a bit weird. Like, let me just disable that. So this point here is very far from any other point in my data set that is also labeled hello world. So when I click on that and I listen to that, that is actually someone rumbling with a bunch of paper. This is not hello world. The segmentation algorithm didn't pick that up. So this is a good case. Okay, this is a problem with my data set. I click view sample, I delete it from my data set, and I continue. And by plotting this here and kind of looking at all the places that are far away from the rest of your data, we can get an indication of what wrong samples are in your data set. Also, if you see that lots of stuff is overlapping here, it might be that your signal processing parameters are not great. But here, actually, if you look at the 3 sets, it separates nicely. So this is probably a good candidate to run machine learning on. So from there, we build a machine learning algorithm. There's a couple of things we do here that will make this more resilient in the real world. One of the most important things here is data augmentation. So probably when I'm speaking and I'm sitting here in my living room and I say hello world all the time, there's very little background noise going on, right? I'm sitting here alone. But if we deploy this in the real world and all of a sudden I have kids screaming in the background or the TV playing, the ML model might not pick up on that. So to deal with that, we can artificially add noise while training this model. And we do that at random all the time. And that helps us reduce overfitting. It helps to make the model more resilient against normal background noise. It's useful. As well, we can mask certain bands in the spectrogram. So let's say that I always say hello world in the same intonation, and then Scott comes along and he says hello world, right? Then that might be something where the model doesn't pick it up because I always say hello world in one go. So we can randomly start masking time and frequency bands. So it doesn't optimize for just the way that I'm saying that. Then we have a neural network architecture, and how you can think about that, that is the number of parameters that we feed into this, the number of parameters in this really large function that we define. So these are the constraints that we set. So after that, you click start training. We spin up a nice computer in the cloud for you, do all these like randomization, trying to find the best matching formula. And in the end, we're presented with this. So this is a matrix that says, okay, for all the times that we had hello world in our data set, we predicted that it was indeed hello world 90.6% of the time. There's a couple of places where the predicted label was noise. That might very well be the issues with our data set that we saw earlier. And a couple of times where we didn't know it. So we can dive into our data set to figure this out a little bit better. But in general, this looks nice. See about 92% accuracy on our set. Once again, we see our inferencing time. Because we already do heavy optimization in the signal processing layer, this is much, much lower. We see our RAM usage and our ROM usage. Cool, so we have a model that works. Let's deploy it. So for both the Bluefruit and the Arduino Nano, you can deploy to an Arduino library. And that gives you a single library that you can implement in exactly the same way as any other Arduino library. It has a bunch of hooks. We have examples for dealing with accelerometer and microphone on the Arduino Nano 33BLE Sense. But we also have examples on using this with computer vision, if you want to use a camera to detect things. Built like a really cool Christmas tree classifier model the other day. And also with all the anomaly detection and regression blocks that you might create. If you work with a different board, just export as a C++ library. You get all the source code. This compiles on anything with a C++ compiler. No external dependencies. So really nice and easy way to get forward. So I've done that already. So what I have here in front of me is the Arduino Nano 33BLE Sense running our model. And let me open up a serial interface. Hello world. Yum. Yes. Hello world. Hello world. There we go. Misses it sometimes. So cool. We have a model that runs here. So I put it together here in Arduino sketch. Now the interesting part naturally is that I want my my buzz to actually respond to that. So as Scott explained, and I modified Scott's flash here, is we just call the vibrate motor. In our case, we're using motor, I can't remember here. We just want to vibrate one of the motors when the last time that we heard hello world was at most 2 frames ago. And after that, we put it back down. I think the interesting thing here starts when you start doing regression models, because then you can also change how much this thing is vibrating depending on the scalar value that you predict. But already cool here. And naturally, this loop can be anything, right? So if it can be when I heard hello world last, then I want to do vibrate motor 1. If I hear a completely different sound, vibrate motor 2. If I hear that someone is standing in front of my door, etc., etc., etc. So some freedom here. So let's actually pull this together on the buzz, and I hope you can hear this through my microphone. Scott and I tested it beforehand, and that worked. So let's take a look. So I put the on, and now we're restarting the Arduino, and it should connect to the device. Not yet. Let me restart. This is the fun thing about live demos. On my phone. Hello, world. Nope. Right, this is really the last time that I'm going to try this. On. Pairing mode. Cool. 3 blue dots. Now it's not running anymore. Okay, trust me, this works really nicely. Scott has it running on his Adafruit device as well. Yeah. Hello world.
There you go.
Hello world. Cool. All right. It took a little time. This is the reason why we didn't publish the Nano 33B license yet. We'll hope to do that in the next 2 days. But yeah, super easy. So we have examples of running the microphone, connecting to the bus over BLE. That is all handled by the libraries that the team at Neosensory has put out. And with the examples that we're going to be sending around, it's really easy to combine these 2 things and make it respond to literally anything, whether it's audio, vision, or anything in between. So with that, I want a short recap, and then we'll go to the Q&A. First of all, I think for me, the really interesting thing, and I never realized this before I met with the Neosensory team and started collaborating on some of the other things, is that sensory augmentation lets you really feel the world. And I think it's like Scott and I were joking a little bit about becoming a cyborg, right? It allows you to have sensors or have events from the real world or data from the real world all of a sudden augmenting you as a person. And that is a really, really weird feeling. And for me, kind of the first time I put the device on, and the standard algorithm that, as Scott explained, that is used to transform sound into vibration, that is already super weird. And you get used to it very quickly. You hear yourself speaking, and already you can feel your own frequencies kind of on your wrist already. It's really, really cool. And I think that once we have a wider developer community hacking on this, we'll really have the potential of you becoming a superhuman, because you can augment your own senses. Like, do you want to combine this with infrared vision? Great, cool. Stream that to the device, and now you can kind of feel what is happening in the infrared world or somewhere where you can't see, which I think is really, really cool. Also, like, there's only a limited thing that we can do, but your experience and and knowing what you can do in your own field together with ML, that is always going to be a unique opportunity. When I talk to people after webinars or just in our forums, we always realize that we and I think the same goes for Neosensory, we can build tools to make it easy to build these type of models, but combining that with your own unique domain expertise is an absolutely unique opportunity, and now is definitely the right time to get started. This is a super new field, but incredibly exciting. So really go ahead and start doing that and take this unique opportunity. And we'd love to see what you guys are going to be building in the contest together with Neosensory. And yeah, that's it on my side. I'd love to take some questions.
Great. Hi, can you hear me?
Yeah.
Awesome. All right, so we've got some questions that came in. One of the first ones was about just some clarification on the verbiage that you used. Vibration sensor, is that the same thing as haptic feedback sensor?
Oh, maybe if I said sensor, I misspoke. We're not doing any sensing. It's a vibration actuator. So like 4 little vibrating devices are in the wristband. If we want to get really pedantic, they're linear resonant actuators, or LRAs.
Awesome. Great. Thanks. Okay, so then we had a question specifically for Jan. What's your thought on Edge Impulse on MicroPython? Do you think that the T-Flight will be supported by MicroPython soon, for example, on the ESP32?
So yeah, the funny thing is actually, so we don't put any constraints on how you integrate it, right? So the only thing we ship is a C++ library with some bindings, and then you can create the bindings from anywhere. So for example, with OpenMV, they do this super cool Cortex M7 with a camera module on it that runs MicroPython already, and you can build models for that through Edge Impulse. So as long as you as long as you can call our run classifier function from anywhere, you can create some bindings and run that straight from MicroPython, etc. And then what we can do in new silicon targets, for example, in ESP32, that, yeah, I'd love to see a bit what the community wants there and what we can do to make that a bit easier. So yeah.
Awesome. We also had some questions about what sort of microcontroller can be used with the Neosensory Buzz.
Cool. So anything will work with the Neosensory Buzz as long as there's a Bluetooth Low Energy interface. Looking at, I think I have the questions up too. I think they were asking what microcontroller is used on it itself. If that was the case, yeah, no worries, all good. If that's the case, we are running, it's an NRF52, which I believe has a Cortex M4 on it. But at the moment, we only give developer access to the device through the BLE interface. It's something we're considering opening that up in the future, but not at this time.
I think it would be really cool. Like, yeah, I mean, for these models, like what we see, anything with like vibration, or like if someone like moves something, we can even do it in the Cortex M0, but you can do real-time audio processing 6 times a second on an NRF52 class device, which is super amazing.
Awesome. Great. The next question was, how can you make different rumble patterns for different events?
So you can define vibrational patterns sort of however you want. So with our SDKs, and actually even at like an API layer, all you're doing is sending over an array of values between 0 and 255, where 0 means like that actuator should be completely off, 255 is completely on. And it groups them up in groups of 4, because there's 4 actuators on the wristband. So if you send 255, 255, 0, 255, 3 of the 4 motors will be on, like one of the ones in between will be off. If you send over like 0, 0, 0, 0, and then 255, 255, 255, 255, you'd have I forgot to mention this operates on 16 millisecond frames. And if you were to send that, you get 16 milliseconds of the 4 motors being off, and 16 milliseconds of the 4 motors being vibrating at full power. So that's how you can start to construct different patterns.
Great. Okay. And then there was one about asking kind of what you used in your last demo, I think, Jan, if you used the Neosensory SDK for Bluefruit library on Nano 33. This user had tried it and was having some BLE connectivity issues. So they were wondering if it was a problem with their board or something else.
Yeah. So the approach that we took here is that I took the library that Scott's team made for the Bluefruit, and I started using the Arduino BLE library instead. which is used by Arduino itself to run the Nano 33BLE Sense BLE stack. As Scott and I realized, there are a couple of small differences there, and we haven't completely nailed it down, which is why we haven't published the SDK yet. So there's some disconnect issues, but underneath it's the same MCU. So both the Nano 33BLE Sense and the Adafruit board are NRF52s. So there shouldn't be any issues. So hopefully we'll fix this out soon, and you'll be able to build these kind of things on both targets.
Yeah, it's not you. It's definitely not you, Mithun. Yeah.
Awesome. Okay, how's the battery life on the band when you run vibrations based on events?
Yeah, so the battery life really depends on the algorithm that you're running and how often you're running it. So it's heavily application dependent. I can tell you for the onboard algorithm that runs, where it's responding to audio in the environment, and again, heavily depends on how acoustically energetic your day goes. But generally, we get about 48 hours or so of fairly active battery life. I think if you're running an application where it's blasting at full power pretty consistently, you'll probably get, I don't know, probably I would say 12-ish hours maybe or so, probably maybe between 12 and 24 hours, less than a day. If these are lower intensity vibrations and not as often, I mean, we have some applications we're developing internally at the moment where the wristband will last 4 or 5 days. So it's just super heavily dependent on your application.
Great. This one's pretty interesting. There was an experiment where people with high blood pressure were connected to a computer and the blood pressure was represented in the form of a flying airplane. And then the higher the blood pressure, the higher the plane was flying, and vice versa. So the task for people was to lower the airplane, and all of them managed to do it. So basically they lowered their blood pressure by visualizing it. And so this person was asking if you think the same approach will work on the wristband.
From a neuroscientific perspective, if they can visualize it, I would, if that's actually effective, that you can visualize by visualizing it and looking at the airplane, I would suspect you could do this through a tactile modality as well, would be my expectation. Definitely worth a shot. Really cool idea.
Yeah.
Yeah.
Awesome. Okay, what is battery capacity? Milliamps, I think is what that is.
That is a great question. I don't remember off the top of my head. I want to say it's something over 10,000 milliamp hours. I could be wrong. Don't quote me on that. I would have to get you an answer offline if you reach out to us on our Slack. I can totally provide you with that.
Awesome. So I think we just ran out of questions. So if you guys have anything else you want to chat about, or if there's any other questions that people have, you can type them in real quick and we can get to them.
Yeah. So I want to note. So if you thought, okay, this was cool, but Jan clicked through the interface a little bit too fast. We just released something this week. So if you go to docs.edgeimpulse.com, go to the responding to your voice tutorial. There's a link here. And you just click on it and bam, you're in our project. You don't need to make an account. You can just click through everything that you've just seen, including all the data that we collected for the project, as well as through all the intermediate steps. So there's a really, really great kind of starting point if you want to build something that responds to your voice together with Neosensory. You just go to the docs, click the link, and bam, you got the full project going on there.
Great. Well, thank you everyone for coming, and thank you, Jan and Scott. This was really interesting. I always love watching these, and the demos are always good. And I'm so glad you got that last one to work, and it's super exciting. I am looking forward to more of these, and so looking forward to seeing what you guys build in your projects for the contest. So as I mentioned before, it was posted, I think, in the link. The link was posted at the very beginning of the chat, and we'll also be sending out an email at the end with that link to the contest, so you guys can go check that out, as well as the recording for this webinar. So thanks again for joining us. Thanks, Jan and Scott. Have a great rest of your day.
Thanks.
Eddie.
Bye.
Yep.